This is the video for section 9.4 notes, slides 14 through 16. All right, so in 9.4, we are talking about something called L'Hopital's rule. All right, so L'Hopital's rule is used to evaluate limits of certain quotients. So for instance, if I have the limit as x approaches a of some function f of x over some other function g of x, L'Hopital's rule states that when f and g are both continuous and differentiable at x equals a, and f of x divided by g of x has an indeterminate form at x equals a. So of type like 0 over 0 or infinity over infinity, right? Or it could be like negative infinity over negative infinity, whatever, right? Some infinite value over another infinite value, all right? Then we can say that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. Okay, and so the key here is if we know that f and g are continuous and differentiable at x equals a, then we can take the derivative of the numerator and the derivative of the denominator separately. Remember, not the quotient rule. Okay, then we can reevaluate the limit. All right, so let's take an easy example here. All right, so let's say we have the limit as x approaches 2 of x squared minus 4 over x minus 2. All right, so now, obviously, what would we do initially? Well, initially, if we all go all the way back to like unit 1, we would say, okay, well, let's plug it. 2 squared is 4 minus 4 over 2 minus 2 is 0 over 0, right? So it seems like it has that truth. But what we need to do is we actually need to make a pretty important statement. Okay, so imagine that like we're saying, okay, f of x is x squared minus 4, right? So f of x equals x squared minus 4, right? And g of x equals x minus 2. All right, so what can we say? Well, f and g they're both continuous at x equals 2, right? And they're differentiable at x equals 2, right? So it's important that we make this statement, because if this statement isn't made, then we cannot use L'Hopital's rule. So f of x, yes, x squared minus 4 is continuous and differentiable at x equals 2. X minus 2, of course, yes, that is continuous and differentiable at x equals 2. All right, so therefore, right, since the limit as x approaches 2 of f of x is 0, and the limit as x approaches 2 of g of x is 0, right? So if we were to divide them, we would get 0 over 0. So we can say the limit as x approaches 2 of x squared minus 4 over x minus 2 would then be equal to what? Well, we could say the derivative of f over the derivative of g. So the limit as x approaches 2 of. All right, what's the derivative of f? The derivative of x squared minus 4 is 2x divided by the derivative of x minus 2. Well, that's 1. And so now we can reevaluate the limit. So 2 times 2 is 4 over 1. So this answer is 4. Now, we could have done this in the past just by like factoring and reducing or whatever, using that old strategy. And that still works, but there are some limits that could not work that way. We would have to do them this way. All right. So let's go ahead and take a look at some more examples. All right. So the limit as x approaches 1 of x cubed minus 1. All right. Over x minus 1. So first of all, okay, we would want to, just kind of in our head, evaluate whether or not we're even getting a L'Hopital's rule question, right? So we'd say, okay, well, 1 cubed is 1 minus 1 is 0 over 1 minus 1, 0, right? So, okay, so 0 over 0. So then what do we need to do? We need to say x cubed minus 1 and x minus 1 are continuous and differentiable at x equals 1, right? Is that true? Well, of course it's true, right? All right, so since that is true, right, then we would need to say, okay, well, the limit as x approaches 1 of x cubed minus 1, that is 0. And the limit as x approaches 1 of x minus 1, that is also 0, right? So we can say the limit as x approaches 1 of x cubed minus 1 over x minus 1 is equal to the limit as x approaches 1 of what? So now we're evaluating the derivative of the numerator, which is 3x squared, divided by the derivative of the denominator, which is 1, right? Remember, you're taking the derivatives separately. You're not using the quotient rule. All right, so now 3 times 1 squared is 3 over 1 is 3, right? So this limit would equal 3. All right, so that's L'Hopital's rule. All right, so now let's take a look at our next example. All right, so our next example, limit as x approaches pi over 2. All right, so first of all, cosine squared of x. So remember, what does that mean? It means the cosine of x squared. So cosine of pi over 2. What is the cosine of pi over 2? Well, cosine of pi over 2 is 0, so 0 squared is 0. Sine of pi over 2 is 1, minus 1 is 0, so 0 over 0. So what are we going to do? We're going to say, okay, well, is the cosine squared of x and sine of x minus 1, they are continuous and differentiable at x equals pi over 2. What would be an example of something that wasn't continuous and differentiable? Well, let's think about, like secant or cosecant, right? You know that secant is the reciprocal of cosine, right? And if cosine is 0, right, at pi over 2, then secant would be undefined, right? There's a vertical asymptote. Therefore, it would not be continuous and consequently not differentiable, right? So if that was the case, then you would have to, state that this, limit could not be evaluated or something. But they are. So then we want to say, okay, well, the limit as x approaches pi over 2 of cosine squared x, that does equal 0. And the limit as x approaches pi over 2 of the sine of x minus 1, that does equal 0. So we can say that the limit as x approaches pi over 2 of cosine squared x over sine x minus 1 equals what? So now, once again, remember, we are going to evaluate the derivative, right? So we can say, okay, the limit as x approaches pi over 2 of, all right, what's the derivative of cosine squared? It is 2 cosine x times the derivative of cosine, which is negative sine of x, right? Divided by, all right, what's the derivative of sine x minus 1? Derivative of sine is cosine x minus 0, right? The derivative of 1. All right, so now take a look at this. This one, okay, be smart. We can reduce the cosines, right? And so this limit as x approaches pi over 2 of negative 2 sine x over, well, there's still a 1 there, right? And so now we can reevaluate the limit, and we get negative 2 times the sine of pi over 2, which is 1. So negative 2 would be our limit, all right? So you have to make sure you realize we do have to make these statements, all right, so that we can indicate that L'Hopital's rule applies. Now, one thing that you should also do is you should indicate that you're using L'Hopital's rule, right? And so once you say, okay, they're continuous and differentiable, right? So this limit equals 0, this limit equals 0. So we can say the limit as x approaches 1 of this, and then we can just put like a little L with a circle around it, indicating that we're using L'Hopital's rule. Okay, so we can put an L here. All right, so now let's do the next one. All right, so first of all, let's just in our heads plug in 1 squared plus 1. Well, that's 2, isn't it? Divided by 2 times 1 is 2 plus 1 is 3. So this is just 2/3, right? So that's it, right? You don't do anything extra there because, well, you didn't get 0 over 0 or infinity over infinity. And so that does not apply. All right. All right, what about the next one? Limit as x approaches infinity of x over e to the x. All right, so let's just in our heads plug in infinity over e to the infinity. E to the infinity would be infinity. So infinity over infinity, right? So what are you going to state? All right, so first of all, x, is that continuous as x approaches infinity? Yes. Okay, what about e to the x? That is continuous as well, right? And differentiable. So we can say x and e to the x are continuous and differentiable as x approaches infinity. Remember, it's important to say like infinity, that's not actually a number. So you can't say at x equals infinity, but you can say as x approaches infinity, right? All right, and so now we would say, okay, well then the limit as x approaches infinity of x, well, that's infinity, right? And the limit as x approaches infinity of e to the x, that's also infinity, right? And so those two things, well, tell us that L'Hopital's rule applies. So the limit as x approaches infinity of x over e to the x, we can use L'Hopital's rule to get that the limit as x approaches infinity is what? Well, derivative of x is 1 over the derivative of e to the x is e to the x. And so we would get 1 over infinity, which is equal to 0. So that limit would equal 0. All right. All right. So we'll do the last notes in class.